Time value problems. Let's have a look at an example. Suppose that we deposit $50,000 today at 6% compounded quarterly for a 3-year term. Now, naturally, what we like to find out is how much will our value be worth at the end of the 3-year period, or the terminal value. Now, when I'm dealing with a question that has an element of time, what I like to do is I like to construct a timeline, just so I can get a big picture of what's going on. And you can see that right here. So here's today. That's when I deposit my $50,000. And my $50,000 is going to be growing at 6% compounded quarterly. And I want to find out how much my money is worth at the end of that 3-year period. Now, this is referred to as a time value problem. And you can see why it's called time value problem. So you got both elements. You got time, just 3 years, and you got value. You like to know what the $50,000 is worth at the end of the 3-year period. So to do the calculation, what I do is I set myself up with the time value variables, and here they are. There's 5 of them. There's the future value, which is what the value will be at the end of the term. There's the payment stream, so if there's a cash flow stream during your holding period, we would enter it there. N, which is the number of periods. I, which is the rate of return we expect to earn. And then PV, that's the amount that we start with today. Now, the other thing I like to do is, because we're dealing with time value, I like to define how we're measuring time. So, for example, is time measured on a daily, weekly, monthly, semi-annual, quarterly? So you see that we need to distinguish what time intervals we're using. And for that, we look at the way the question is set up. So in this case, we're told that the interest is being earned on a quarterly basis. So the relevant denomination of time is going to be quarterly. And what that means is anything we input into the framework or anything that comes out from the framework will be on a quarterly basis. So you have to be consistent. So you can't be mixing semi-annual information with quarterly data. You can't do that. They all have to be compatible. Now, the other thing I like to distinguish when I'm doing a time value problem is the direction of the cash flows. And here's what I mean. Your calculator needs to know if the $50,000 is a cash inflow or an outflow. And similarly, at the end, we need to distinguish whether this amount will be cash inflow or cash outflow. So the trick I use for that is as follows. I simply take the wallet point of view. So you just have to picture what's happening to your wallet as you enter each of these values. So in this case, because we're depositing money at the bank, what's happening to your wallet? Well, if I walk into the bank and I gonna deposit money, that's money coming out of my wallet, so therefore we would enter it as a negative. On the other hand, at the end, when I take my money out from the bank, then that money comes into my wallet and you could see it'll be a positive number. So those are the only 2 things you need to remember, ladies and gentlemen, is so when it comes to time value, first you have to define how you're measuring time. And the other thing is you have to take the wallet point of view in order to distinguish between positive and negative cash flows. So once you've set up, so once this is all set up, and once you have your reminders here, now you can enter the values. And let's see how it's done. Well, let's start with a 50,000. So first of all, that's happening today. And because we're depositing the 50,000 at the bank, that's money leaving my wallet. So that's going to be negative. What's next? The return that is going to be earned is 6%. Now, if you enter 6%, that would be the wrong answer because everything has to be on a quarterly basis. So 6% quarterly, that means 6% spread out over 4 quarters during the year. So that works out 1.5% per quarter. Now, the term is 3 years. And if you enter 3 for N, you would get the wrong answer, because 3 is annual. You have to convert that into quarterly basis. So there's 4 quarters in a year. So there's 12 quarters during this 3-year term. And in this case, there are no payment streams. In other words, we're just making a lump sum deposit today, and we just want to know what it's worth in the future. In other words, there's no cash flow stream in between. So we just leave it 0 or just don't enter anything for payment. And then we just solve or compute for future value. So that our calculator will do the rest. They'll say, okay, 50,000 growing at 6% compounded quarterly will be worth 59,781 at the end of that 3-year period. So now let's look at a second example. Suppose now we invest 100,000 today at 3% compounded monthly for a 2-year period. Once again, they want us to find the terminal value. And once again, we go to our frameworks, right? So if you're dealing with time value problem, let's take out a timeline so we can get an aerial view. There's the $100,000 investment. It's growing at 3% compounded monthly, and we want to know what this will be worth at the end of the 2-year period. So to do the calculation, we need our time value variables right there. So at first, ladies and gentlemen, don't even look at the values. First, you got to set yourself up. So here's the 5 time value variables, and then we have our reminders here. The first reminder is what denomination of time are we using? In this case, it's monthly. And the other reminder that we need is that when we enter these cash flows, it has to be from a wallet's point of view. So if the money's leaving our wallet, you enter it as negative. If the money comes to our wallet, it's a positive. Only once you've set up your time value variables and you have your reminders, now you can start inputting the values. Okay, so here we go. So start off with today, we're investing, so that's money leaving our wallet, so that's minus 100,000. What's the rate we're going to earn? 3%. Yeah, but it says monthly, so 3% is annual. So we got to divide it by 12. So it's you're earning 0.25% per month. How long is the horizon? 2 years. Yeah, but monthly. So multiplied by 12 months. So that works out to 24-month period. Once again, there's no payment stream, so we just compute for future value at the end of 2 years. So there it is. If our 100,000 is growing at 3% compounded monthly over a 2-year period, at the end of the 2 years, it'll be worth 106,176. And notice that the calculator will spit out a positive number because, again, if you're using a wallet point of view, at the end of the investment horizon, you cash this money out. In other words, you sell the investment and the money comes in your wallet. Now, notice the other thing I did here is, because future value is generic, like future as of when. How future are you looking at? So what I always like to do when I'm looking at future value or even present value, notice I did the same thing here. I indicate future value as of when. So this is future value as of year 2 or at t equals 2. Whereas PV, I'm trying to find out what this thing is worth as of today. Let's look at a third example. We invest $25,000 at 5% compounded continuously for 2 years. Once again, we like to see what the terminal value is. Now for this, because it's continuous compounding, I'm going to show you 2 approaches, and you could decide which one works better for you. The first approach is to simply convert from continuous to discrete, and then just use a discrete rate to calculate the future value. And the reason I say that is because for a lot of us, maybe we haven't seen this in a long time, or maybe we haven't seen it at all, right? Because that's the continuous compounding framework. So why don't we get rid of the continuous compounding and just express this return on a discrete basis, and then we just work with that. So let's see where this leads us. So step 1, we want to convert from continuous to discrete. So there it is. We plug in 5% continuous compounding over here. So that's 0.05 in decimal form. And so when you plug that into your calculator, you get this number. And then, of course, the ones cross out. So therefore, the discrete return is 5.1271. So rather than looking at 5% compounded continuously, we have the equivalent, because they are equivalent. The equivalent is 5.1271 without compounding. And that's what discrete means, without compounding. So once we have that discrete rate, discrete annual rate, we're back to our usual frameworks, right? So those are our time value variables. And in this case, we have an annual rate because we did the conversion. We went from continuous compounding. To discrete. So now we can use the discrete rate to solve this time value problem. And because it's annual, that's going to be our denomination for time periods. So here we go. Enter the values. So we're investing $25,000 today. It's right there. And remember, that means money's coming out. What's the rate we're earning? 5.1271 on an annual basis. For how many years? 2. Is there a payment stream in between? No. So you just leave it blank if you want, and then you just compute for future value at the end of the 2-year period. It would work out to 27,629. Now the second approach we can use is the following right here. So we've seen this framework before. This is for the discrete. So future value is equal to present value compounded at the discrete rate by the number of periods in the horizon. And at the same time, we know the relationship between continuous compounding and discrete return is as follows, right there. So what we're going to do is we're just going to combine the two. How? Well, see the 1 plus r here and the 1 plus r there? So that's exactly what we're going to do. So where we see 1 plus r here, we're going to substitute it with this guy right there. And that's what we do. So when I bring this down, instead of 1 plus r, I just plug in e to the x. So see that? From here, you say that's equal to that. So again, where you see 1 plus r, you just plug in e to the x, and that's it. That's all there is to it. So then you plug in 25,000 today, and here's the e, right? Exponential, and x is the continuous rate of return, which is 5%, and then you multiply it by the t, which is 2 years, and then you just carry that down, and you'll get the exact same answer as we did using the discrete approach.